Very good evening to everyone. Good evening, Dr. Swati.
Good evening.
And I would like to say good morning to you. You have woken up so early just for us. Thank you so much, first of all, for accepting our requests, Dr. Swati. Students, I request all of you to join us for this session. And we have many who are joining, so we keep allowing them to join. Um, Meanwhile, for those who have just joined us, and even to Dr. Swati, I'd like to give a short introduction about ourselves, and then I would like to introduce Dr. Swati Mohan to everyone, and then I would let Dr. Swati to take over and share her experience with all of us. And at the end, of course, we're going to allow you all to ask questions. So we would want you all to listen to the talk to I mean to the topics that she's talking very carefully. Okay, so again, I welcome everyone. I'm Nikita, co-founder of SSERD and Space, where we provide space education for students from schools to universities. At the same time, everyone, those who are interested in space, including those who are looking at changing their career from whatever they're doing to the space sector. We have been working with students through several programs, and Girls in Space is one of our initiative, one of my favorite initiative, uh, because this was in the very beginning of SSERD, that when we were conducting program, I saw very few girls in the programs, or sometimes I saw no girls. Like there's literally no girl; it's all boys. And I'm like, why is this? I wanted to see girls. And then I'm like talking to everyone, and they say, no, probably space is not for girls. There's no opportunity. Girls should not do this, should not do that, or there's no role model. I'm like, okay, now I have to do something. And I thought for several times, several months altogether, and I decided, okay, you know what? Let's do something, and we call it just. In fact, the program name back then, the very first program that we did was Girls and Women in Space and Astronomy. I still remember. It's a long name, but then we decided, okay, we want the future generation to come and explore the space. So we made it short, Girls in Space. So from 2018, we've been doing this program, Girls in Space, and we call all the girls to learn about space, to understand what are the different domains that are there, and to also explore the real, or like let's say, just to in simple words, the role models. You can find your role models here, because you would think, no, this is not possible for a woman, or you would have heard. But here in this program, we give you examples of women who thought of same thing just like you, at your own, I mean at a similar age like you, and they went on to achieve it, right? So that is what this program is all about. At the same time, Aerospace camp is our summer camp, where we allow all the students to come join in person and learn about space through hands-on activities, and it's open for everyone. These are two highlighted programs, but we conduct several other things. I'm gonna not, I mean, I don't want to share about everything, but let's focus on the program for the day. I saw several of you just joined. Again, I welcome you all to the talk, which we have by Dr. Swati Mohan. Before I hand it over to her, I would like to introduce Dr. Swati to all of you. So, Dr. Swati Mohan is a distinguished aerospace engineer and a leader in the field of space exploration. Currently, Dr. Swati Mohan is serving as the technical group supervisor for guidance, navigation, and control systems engineering at NASA's Jet Propulsion Laboratory. Dr. Mohan brings a wealth of expertise and passion for advancing humans' reach into the cosmos. In fact, Dr. Mohan's career in space science began very early, which she would be sharing. But what we've heard is that she got inspired by her love for Star Trek. This is like a show, and solidified through her high school internships at NASA centers, including Goddard Space Flight Center. So if you can see, she has been interested in space at a very young age, just like you all are. Okay, and Dr. Mohan has continued to, work on her. I mean, one of the space topic that she worked during her PhD is to work on autonomous assembly of space telescopes. Okay, and then remarkably her thesis experiments, that is fierce, that is synchronize position, hold, engage, reorient experimental satellites, was tested aboard the International Space Station. Dr. Mohan has contributed to several landmark NASA missions, including Cassini spacecraft's exploration of Saturn, the Grail mission mapping the moon's gravity field, and most notably, Mars 2020 Perseverance rover. As the guidance, navigation, and control systems engineer for Perseverance, she played a pivotal role in its successful landing on Mars in February 2021. There's so much that I could say, but I would now request Dr. Swati Mohan to take over and share um, your journey. I mean, how did it start? Where did it begin? What are the steps that you took? And how did you reach where you are today? And of course, we want to hear about some of the missions that you have worked on, which our students would love to hear about. Dr. Swati, I now hand it over to you.
Thank you very much. Thank you for inviting me. I'm really honored to be a part of this program. Definitely something that I wish I had had when I was a little girl. As Nikita mentioned, back when I was a girl, there weren't a lot of women role models in space, right? This was before the time that Kalpana Chawla had gone into space, before Sunita Williams in the mid 1980s. So when I was a child, actually, it was somewhat understood that as an Indian child, when someone asks you what you want to be when you grow up, there's probably only two right answers. You're either a doctor or an engineer. So I didn't know what being an engineer meant at that time when I was like 5 or 6. So I'd gone to the doctor, so I knew what a doctor did. So a very long time, I I thought I wanted to be a doctor. I was actively pursuing being a physician for most of my childhood until I was about 16. That's not to say that I didn't like space. I very much did. My first exposure into space was through the television show Star Trek: The Next Generation when I was about 8 years old or 9 years old. And I remember seeing the images of space from that TV show, of the different moons, the nebula, and it got me interested in space. So I would go to the library and check out books to learn about space. But Star Trek fundamentally is science fiction, right? There's no it's set in the future. It's a land of make believe. So even though it introduced me to space, there was no jobs that I could see on there that I could aspire to, right? These were all way in the future. So it was a fun thing, just like an extracurricular hobby that I was interested in, but I never thought of it as a possible career path. So for the very longest time, I was completely focused on being a physician. I would um, do extracurricular camps associated with that. I would try to volunteer at the hospital. I would shadow my aunt, who was a physician, to go work with the patients. It was um, my 11th standard, I took physics for the first time. And this was the first time that I got a taste of what engineering was. So in biology, which I had already taken at this point, there's a lot of memorization that you have to start with, right? Memorization wasn't really my strongest skill. I mean, I could do it, but I had to spend a lot of time and energy trying to uh, get all of the facts and all the parts of a cell memorized. I wasn't that great at dissections. My hands weren't necessarily as skilled, and it wasn't something I enjoyed for dissections. So coming into physics, suddenly there was this class where there was only one thing you needed to know. F equals ma, force equals mass times acceleration. And the entire year, that's the only equation that we needed to know. And it could describe so much of the natural world that was just astonishing to me that you could describe almost all motion with just this one equation. How to visualize objects moving, how to visualize forces acting on a body came pretty naturally to me. It was enjoyable to me to learn about the physics and be able to apply that particular equation. I was still not 100% sure about going into engineering, although taking this physics class, having a really good teacher in that physics class started to sow the seeds of doubt of whether or not I should go into biology when physics was so much easier for me. Um, the summer after my 11th standard, I went to space camp, maybe pretty close to the Astro space camp that Genix does. It was a completely in-person event in Huntsville, Alabama, next to the NASA Center, Marshall Space Flight Center. And it was a week-long program where in the mornings you had lectures about different space science topics or different history of space space flight, and then you got to do these hands-on projects in the afternoon. One of the hands-on projects that we did was a simulation of a mission where they had a pretend mission control and they had a full scale um, portion of the space shuttle that they had built in their base. So we actually pretended that we were astronauts on a real mission, and we rotated through the different roles. So you could either be in mission control, you could be one of the commanders, or you can be one of the scientists in that mission. And we got a chance to do all three roles. So this was the first time that when I was in the mission control seat, um, this was the first time where suddenly it felt natural. Like there was something about this job that it connected for me. Like, oh, this is an actual job that one can aspire to. That there are people who work in mission control. They're not the super elite astronauts who go into space, but it's a real job that's important to the mission. I could probably do this job of being in mission control. There was suddenly an example of a career or a job in the space field that I could aspire to. And having that um, role model of having that awareness of a career path that would allow me to combine my love for space and pair it with the engineering that I was naturally better at than the biology. It caused me to really think hard of, okay, what is it that I really wanted to do? And then make the decision that I was going to switch into going into aerospace engineering. So this was just before I started applying for colleges. So I looked for colleges. Oh, sorry. One more thing. That same summer, like 2 weeks after I went to space camp, I was curious about space. So I happened upon an internship at Goddard Space Flight Center, which was about an hour's drive from my house. It was an unpaid internship for 3 weeks where they just needed some people to do some computer designs for some of the paper things that they had. The actual internship was very boring, but while I was there, they had this model rocket contest. So the other interns and I, who for the first time happened to all be girls, it was the first time that I'd actually met any other girls who were interested in space, just like I was. So we worked on this model rocket that you can see here. That was our very first. That was my very first rocket that I ever worked on, and just the process of building it, of going through the design process, of putting it together, testing it, seeing what didn't work, and then coming back and fixing it. That was so fun that I was like, I can do this. This is something that I can do, and it's enjoyable. I would want I would want to do it going forward. So I decided to go into aerospace engineering, taking the rocket and the space portion of it and the hands-on building. I looked at a lot of different universities. I chose Cornell University for my undergraduate. At the time that I went there, Cornell was very heavily in the space field. They were working with NASA Jet Propulsion Laboratory on the Mars Spirit and Opportunity rovers. So they had rover programs for undergraduates where you could do that at the school. They also helped to run the Arecibo telescope. So I chose it because I wasn't sure if I wanted to do pure space sciences or engineering of actually building things. And Cornell let me have the opportunity to try both if I wanted to. So I graduated, I decided to do engineering. Um, and the undergraduate research project that I had was building a little satellite with building the attitude control system for the satellite. So making sure that the satellite was pointed correctly, that it didn't, start tumbling when it was in space. So because I was still new to aerospace engineering during my undergrad, I tried a lot of different things in a lot of different areas in aerospace engineering to try to find the one that I liked the most. Because even though people think aerospace engineering is a pretty narrow field, there's actually a, a lot of different things that you can do with it, because fundamentally aerospace is an applied field where you're taking all the disciplines of engineering and you're applying it to the space environment. So you need mechanical, you need electrical, you need chemical in some sense. So you need all of these different fields. So then it becomes a super large um, area to expand. So I kind of tried bits and pieces that I thought. My first internship was at Kennedy on um, astrobiology. Actually, it was building things for growing plants in space. I thought, like, oh, I had wanted to be a doctor for so long. Here's a way of doing um, biology thing in space. That must be the perfect fit, right? No, this was definitely not the thing for me. It was a fun experience. Loved working at Kennedy Space Center and then NASA family and how cool it was to work there. But decided no, I don't need to do anything biology, and I like firmly dropped any biology botany possibilities at that point. And then my next two internships were at the Jet Propulsion Laboratory. The first one was at Caltech, and it was with a group called TMEX, which is a concurrent design engineering group. So what they do is they get a bunch of experts into the room for about a week, and they design these missions to go, to go and do different things. So the summer that I was there, we were in charge of designing missions to go to Uranus and Neptune. How is it going to get there? What's the science it's going to do? How long is it going to stay there? And like figuring out all these things. And that to me was really cool. Like that was the exploration part that I liked about Star Trek, where you could go to these different worlds. You could figure out how you were going to get there and what you were going to see. It was um, that was part of it. We don't know what's there, so let's go find out what's there. So based on that experience, I'm like, oh, JPL must be must be the place for me. So I did whatever I could to get another internship at JPL the following year. Um, and I was put on a project on Mars where I was analyzing images of um, different areas of Mars and characterizing them. So this picture of Mars that you see in the corner, you can see little black streaks here. Um, these are what's called recurring slope lineae. It's basically streaks on the edge of a crater rim where there's a slope. Um, so my job over hundreds of images was to count the number of these black lines, how long they were, how many pixels across, like if they spread out and branched into multiple things. Um, Super boring internship to the point where after that internship, I'm like, I don't think I ever want to see another image of Mars again. And firmly basically decided like I don't need to be a scientist. I'm happy building things. At least I get to, see it work. But the interesting thing about these pictures, so some 15 years after, with, I mean, I only contributed whatever 4 weeks during the summer, but many, many years of images of people like that doing that painstaking work. These images were part of the reason that scientists were able to say that there's current liquid water on Mars. These are um, brine solutions that have actually flowed down the hill of this crater wall. So after painstaking, meticulous calculations of seeing the same images year after year, they could actually track that these were growing, and it was part of the evidence that they were able to use to say that there was water on Mars, which is a huge deal, right? Um, but when you're doing it, it's you don't necessarily see that end product. It takes so many years to get to that end product. So in science and engineering is a little bit different, and this internship was kind of pivotal for me for understanding what that difference between um, where you get the what you need to feel gratified in working on a project, and that's a very individual thing, and how that plays out in the particular field that we're doing. So out of all these internships, I realized I loved JPL, the Jet Propulsion Laboratory, because their whole premise was robotic exploration of the solar system. So it was all about going out and like seeing what was there, and it was for doing science. And then I liked the research that I did at Cornell with the attitude control system, because I was actually like building things and coiling things and able to test things. So I was like, okay, maybe I should put those two together. Um, with control systems, it's a very math heavy discipline, so you don't get as much into it in undergrad. So I knew if that was right, I had to go to graduate school. So I went to MIT for my graduate school. My advisor for the undergraduate research for the satellite, he had gotten his PhD from the same lab that I went to for graduate work. So I knew that it was an area that would fit fairly well, and he was able to make a couple of phone calls so that um, my advisor actually saw my application. Part of this then was luck. So I worked on these spheres, which are these three like ball-shaped satellites that are inside the International Space Station. They were actually supposed to fly on the mission just after the Columbia accident, the one where Kalpana Chawla and six others passed away. Because of that accident, they grounded all space shuttle um, activities, so they didn't fly. And then 2 months, 2 months after I joined MIT, we got the phone call saying, "Okay, your satellites are ready to fly. Pack them up, send them to us in 3 weeks. They're gonna go on the next shuttle up." So that part was 100% luck, right? It was just timing of, what had happened and when it would be that I happened to be there at the time where they were just launched. So because of that, I was able to work on that for my PhD. And I actually had data from space, from inside the International Space Station, as part of my PhD. And that whole process of working with the astronauts, sending the code up there, analyzing the data, testing it, it was basically like a mini mission that we got to iterate. So I learned how to operate a spacecraft in space. I learned testing procedures. I learned how to, communicate because I was one of the two that were picked to actually train the astronauts um, on this experiment. So it was a lot of different skills combined that was super exciting to work on during that time. So I graduated from MIT in 2010, and then I came to work at JPL. Between undergrad and grad, I'd actually taken off a year and I'd worked on the Cassini mission. This was also one of the luck timing portions of it. So when I finished undergraduate, I got an offer to work at JPL on Cassini. Um, and that next year was when Cassini was going to reach Saturn. So of all of the times to work on the mission, this was probably the most exciting. And Cassini was a huge, like a flagship JPL mission. It was conceived the year I was born. It launched when I was still in high school. It had a 7 to 8 year cruise to Saturn, and here I was at the very end of it, getting a job right as it's getting to Saturn, to be a fly on the wall. So my job on Cassini was very low level, right? I was taking notes at meetings and um, basically being a runaround and just kind of documenting things that other people were doing. But it was a fantastic experience to see how those type of critical events are prepared for in order to make sure they go smoothly because you only get one chance for most of these in space, and if you don't do it right, it doesn't come around again. Like it would have flown past Saturn or it would have, crashed or things like that. So it gave a lot of experience that I used on the Spheres mission of how to prepare for these different um, big operational events. After I came back from grad school, I worked on a mission called Grail. So Grail was first of its kind. It was a formation flying mission around the moon, which means that it wasn't just one spacecraft; it was two spacecraft, and they were doing a very tightly coordinated dance as it flew around the moon. And the science that it wanted to do relied on the two spacecraft being perfectly coordinated with each other to analyze the measurements. So I learned about how to figure out where spacecraft are in space, the techniques that we use to figure out where they are and where they're going, and predict where they're going so that we can know whether we're doing the right science or not. So that was a super fun mission. I was on it just at the very end of just before it launched to when it got to the moon. So not very long, but a lot of learning in that time period. The next mission I worked on was optiques. This was a telescope assembly mission, which I was super excited about because it was very close to what my PhD thesis was on. I was like, this is fantastic. I get to work on basically seeing my thesis come to life only a few years after graduate school. Um, in the end, it didn't work out. This was one of the missions I worked on that was canceled. As in, we got to a particular point in the design, and then NASA decided that it couldn't afford the rest of the mission, or it didn't have a customer who really wanted it. So um, it never ended up actually getting built or tested or anything like that. But I still like talking about it because it was so close to my PhD thesis. And maybe one of these days in the future, we'll be ready for that type of telescope assembly, if not now. Um, Optiques was supposed to be a telescope that was attached to the International Space Station as a payload. Um, so after I worked that mission as a payload, I went to another one called OCO3. That's the Orbiting Carbon Observatory number 3. And OCO3, it was basically they had just launched the OCO2 mission, and they had a spare instrument. So they thought, oh, we already have a science instrument. Let's just put it in a package and send it. We can get 2 for 1 type of thing. Um, it it was a great concept, and it was pretty cool to work on. But it was one of these missions where it was a lower priority for NASA. So we got to a certain point, and then they said, okay, well, we don't need you to work on it right now. So they bathtubed. They sent a lot of people home, and they weren't working on it. And then 6 months later, they're like, oh, work on it again. And they kept doing these ups and downs for the mission. So it did eventually end up flying, but because it was doing all these ups and downs, I didn't stay on the mission throughout the entire project. I left to go work on Mars 2020 Perseverance because otherwise I would have missed that opportunity. So I chose to leave OCO3. In 2013, I joined the Mars 2020 mission. This was shortly after the Mars Curiosity rover had landed successfully. And based on that, people were super excited. They were like, oh, we have a lot of spare hardware left over from Curiosity. We should just build a copy of Curiosity rover, and it can do more science. So that's how Mars 2020 started. Uh, I worked on Mars 2020 from almost the very beginning of that project to through landing day and a little bit above. So out of all the missions I've worked, Mars 2020 I've worked for the the longest consecutive period of the mission itself. So I didn't leave and come back. I didn't go. I worked consistently through the inception of it, through building it, through testing it, launching it, all the way till when it landed on Mars. And because of that, as one of the few people who did that, it was a really rewarding um, process because when we work early phase versus late phase, like you don't realize sometimes the decisions that you made, years before on paper, what implications they will have when you actually have to build it. So this was a really good way for me to work a project through the entirety to be able to see, okay, I made these decisions really early in the project here that those decisions had implications when I went to test it. Those decisions had implications when I'm flying it in space. And understanding how those decisions, how that architecture works in every phase of the mission, I think gave a much better perspective for me afterwards to be able to say, okay, this is what's important in this phase that you need to think about years ahead so you can set it up earlier and be able to think about that whole design, not just the immediate focus of where you are right now in that mission. Um, so for Mars 2020, I worked primarily cruise and entry, descent, and landing. Earlier in the mission, when we were a smaller team, I did work the surface operations part as well. And then when we got to like actually building it and testing it, it was just too much scope for one person to handle. So I offloaded much of the surface stuff to other people on my team because I wanted to make sure I did one thing or two things right instead of trying to take on too much responsibility. So that was March 2020, and then the last one that I have on here as a picture. It's called the Small Satellite Dynamics Testbed. This is actually a testbed that I founded at JPL. So when I was in undergrad, I had worked on CubeSat missions. At that time, CubeSats were just coming up. Like the mission that I worked on was like the second or third launch of a CubeSat ever. By the time I got to JPL, it was now starting to be a little bit more pervasive. So JPL was looking at doing CubeSats, and the way you do CubeSats is very different than how JPL is used to doing missions because they in these big missions they start from like what do we need it to do? Okay, let's design it to do that. Whereas in CubeSats, you have a almost already designed box. So it's more of what can we get this box that's already designed to do versus designing one from scratch. So one of my colleagues and I basically pitched this idea of having a dynamics test bed, so a place where you could actually put the satellite on an air-bearing floor or air-bearing to actually get frictionless movement so that you could test the control systems um, in real time without having to simulate it. Because most of the big spacecraft, they're too big to actually move here on Earth, but the CubeSats they are. You can move them. They're only not like this big. So and then that means you can test the actual thing um, that you're flying. So we basically talked our way into getting this test bed founded at JPL and basically made it into a little institutional resource to bring some of that test as you fly small satellite um, paradigm thinking to JPL, which had primarily been big spacecraft type of thinking. So I put it on here as an example of um, it was an idea that my colleague and I came up with. Nobody asked us to do it. Nobody, um, supported us so much to do it. But it was an idea that we came up with, that we talked to the right people, and we were persistent in getting it founded because we saw the need and we saw a particular solution. Um, so even though it's not part of my day job, I do take a lot of pride in being able to show that we got that founded and how that's been able to help different missions at JPL. Um, I think that's basically all I wanted to say. There's kind of three big lessons that I've taken away from looking back on my journey. One is to be honest with yourself of knowing and accepting who you are, what you like to do, what you're naturally good at, and trying to find uh, a career path that really leverages those things. Because when you can find a career path that takes what you really like, your passions, and pairs it with skills that you're good at naturally, it just puts you in a really good position to succeed. The second is to create your support system. These are the people around you. I couldn't have gotten where I am without really good mentors, advisors that helped me with make those phone calls, and then my parents and my friend system in order to keep going. Because it's easy for me now to look back and say these are the parts that I saw, but when you're in it, you don't know where that path will lead. Every step takes you further on the journey, but unless you keep taking those steps, you won't necessarily get there. So it's important to keep taking those steps, and the support system is really critical in giving you that motivation and foundation to keep moving forward uh, in that vein. Um, Oop, backwards, wrong way. And then the third one is to actively do your best. A lot of the opportunities that I had, they were kind of mixed, right? Some were ones that were known that I could research, that I could apply for or sign up for, like the space camp or the internships. But there were others as part of them that uh, were not as clear, and it took me asking or showing initiative to do those things, like founding the small satellite dynamics testbed, even the rocket project that I worked on at Goddard. Right, it wasn't something that was part of the internship, but because the other interns and I wanted to do it, we asked um, our advisor if we could do it, and just the sheer um, amount of asking got him excited. He like took us and got us all the supplies and helped teach us how to use the machine shop and how to put together that rocket. If we hadn't asked, we would never have gotten that opportunity. The same when I was in undergrad, I asked to present at a conference. It wasn't really expected of undergrads at that point, so my advisor, it hadn't even occurred to him that we should do this. But being able to do that as an undergrad gave me the practice and the confidence because I'd already gone through it a couple of times by the time when I got to grad school, and it mattered. So it wasn't as scary of a process. And it helped build my resume to look good for things like grad school or jobs. So um, there are the opportunities that are clearly labeled, and then there are the opportunities that are not, right? And you, by actively trying to do your best, you keep pushing what you want to do, or just keep trying to be curious, and you never know where that will lead you in creating opportunities for you that didn't necessarily exist in the first place. Oops, backwards. Yep. So knowing yourself, choosing your support system, seeking out opportunities in line with your goals. Coming to something like this is actually um, very, very apropos for that type of advice. And then don't give up. Right? I could never have imagined when I was your age of where I would be. The path is not clearly laid out. It's easy to see looking back, but it's a lot of individual steps going forward. It was a lot of decisions that I had to make with not so much information, and just taking a chance on what it was going to be and hoping it worked out, or to keep trying even if one decision kind of went this way. Just keep your eye on the prize and keep trying. And that's all I had. I can take any questions. You guys have any questions?
Yes. Dr. Swati Mohan, thank you very much for sharing that remarkable journey that you had. In a way, when I was listening, one thing that I saw was you went on to create an opportunity for yourself. Point one. Point two, I saw whatever small things that you started off with, um, it came back to you in support, when you were working on a bigger mission. And that's what we actually don't think of, or nowadays students think of, that this is very small, how would this be helpful for me later? But you'll never know that one day it'll come back and it'll help you in a bigger way. It adds experience, and it adds experience in a way people will be surprised ki, you worked on this long back. I mean, it's important now. So I see that that came to help in a bigger way. And it's very amazing to know the missions that you worked on, and everything about you. I would now ask everyone to raise your hands in case if you have questions, and I'm gonna see how many of you have questions. Um, and you can also go on to type the questions in the chat, students and all the audience here, so that we can pick the questions from the chat as well. While Okay, so there are already questions that have come. You can all go back, I mean, you can all go on to put the questions, but at the same time, I would allow you to ask questions as well. So, Krisha, you can unmute yourself, and I request everyone to stay on mute, and then we go one after the other. Krisha?
Yes, good evening, Dr. Swati Mohan. I'm Krisha. I'm a grade 12 student. And before I ask my question, I must say I'm so excited. Like after listening to you talk, I'm so excited for possibly the projects I can work on in the future because this is a field I'm very interested in. So my question is a little more general. What do you think of the future of the aerospace engineering field? Do you think missions in the future are going to be centered around a particular cause, or do you see a change or a change in trajectory of the goals for all these certain missions? And also, what subfield in aerospace engineering do you think is going to be the future?
So there's kind of two camps that I see coming up in aerospace. There's the uh, smaller, more efficient um, missions that are really focused on uh, getting access to space in the Earth Moon system faster, cheaper, better, easier, that type of thing. So there's a lot of work going on to build out that infrastructure um, in low Earth orbit in the Earth Moon system, right? And that's all about like in space manufacturing or multiple launches or space stations or lunar bases, that sort of thing in the Earth Moon system. And then there's the other part that's still ongoing, but maybe not as um, prevalent, which is still the outer exploration, the bigger telescopes, the going to the future of to explore Uranus or the Kuiper belt objects or things beyond our solar system. I think the balance between the two is starting to shift. So it used to be that they were about equal, or the exploration part, like the International Space Station and stuff, was um, more. But I think we're kind of at a precipice where the space industry is kind of taking off with all these startups, that the Earth Moon system will be very much larger part of the space ecosystem than it was in the past. In terms of what career fields are really coming up, it's hard to say because um, there's a lot of emphasis on autonomy right now, but autonomy is, I see it more as a tool, as an enabler, not a field in it of itself, right? There's aspects of the space field that you always um, have to deal with because of the environment, right? The thermal properties, um, the temperature differences, right? So autonomy can help you in executing some of those missions, and maybe it's okay because some of those have been solved for the small Earth Moon system. But eventually, if we want to send people farther, those type of core disciplines, whether it's mechanical or civil or electrical, propulsion, you have to make advances in those core disciplines to actually take um, a jump in the space field. Does that help answer your question?
Thank you
Thank
so
you.
much, Doctor.
Thank you very much. I now request Harini to ask a question. I see you unmuted.
Good evening, ma'am. My name is Harini. I study in grade 6. I was very inspired by your talk and your journey. So, I just wanted to ask, you worked on the Mars rover mission in 2020, right? 2020.
What are
Uh,
the Mars rover missions in general, or what was the last Mars mission?
I think the last one, I guess, the Perseverance. So, how was your experience there, and what did you exactly do there?
Yeah, so Perseverance was the first leg of Mars sample return. So its mission was um, to go to Mars, to a place that we think held the signs of past life, and to collect samples for eventual return to Earth. Perseverance itself is not coming back to Earth, but we hope those samples that it's collected will come back to Earth. My part of it was the guidance, navigation, and controls. So it's basically the eyes and ears of the spacecraft. So during the cruise from Earth to Mars, we made sure that the vehicle knew how it was pointed, that it was pointed correctly to point its solar panels to the sun, that it was pointing its antenna back to Earth, that it was set up correctly to do the entry, descent, and landing. And then during entry, descent, and landing, it's a very technically challenging time, because it takes only 7 minutes to get from the top of the atmosphere down to the ground. It takes 11 minutes for light to travel from Earth to Mars at the time of landing. So everything about entry, descent, and landing was completely autonomous. It had to figure out where it was, where it needed to go, how it needed to point, what it needed to do, what it needed to, throw off, how it needed to slow down. All of it had to do all on its own. So I did a lot on helping on that portion of the system, doing testing on that portion of the system, making sure that a lot of the sensors worked correctly for entry, descent, and landing. On the surface side, I helped with an area called autonomous navigation. So in order to collect the samples, the rover has to drive a lot. Like it has to go, and find where the interesting samples were. So if we have to tell it every step that it needs to take, it would take forever for it to go. So we worked on a technology called autonomous navigation, where it could take pictures and then drive based on what it saw in the pictures to figure out where it was, and to make sure that it was all safe as it was driving through these different rock fields. So I worked on that on the surface side a little bit also.
Thank you very much.
Perseverance has now been there for more than 3 years, and has collected its samples, and is now kind of going around and doing science in its extended mission, and waiting for the next missions to come back and pick up the samples.
Right. I see two questions which is kind of overlapping, so I would merge together and ask. So there's one question with AI revolutionizing fields like image analysis and crater detection. How is it shaping the future of space industry? What skills should we focus on? And there's another question which is again on AI. I've heard many people say that in few years, when AI will take over the world, there wouldn't be any space scientists, but instead there would be robots. Is that true? Can you like put together an answer? It's a wonderful question, I feel.
It's a wonderful question, and I think of AI as a tool, right? In the same way that computers replaced slide rules, AI will replace the way that we do things now. And it's not to say that there won't be space scientists, right? That there won't be engineers, but the way in which you'll do your work is different, right? So the human part of that is, what are the questions that we want to ask? What are the things that we want to know about where we're going or what we need to build? And AI can help us be better at refining what those questions are. It can help us find unique solutions to that may tip in into a different industry, because if we design, there's no one way to design a mission, right? Like even if it has the same objectives, you can find like 50 different solutions that will work for that particular mission. And it's all about the people who came up with the designs, how they think, how they came together to find a solution, which is why we need diversity in our teams. But in that same vein, if you look at the space, what you can find as a solution is based on what you can see and understand. If AI lets us span more of that space to find some more unique solutions, we may be able to do more, right? And using that, we may be able to, go farther into space, see more, get more data down, be able to understand the universe quicker, right? That turnaround time between getting one batch of data, asking the next question, and sending the next mission to answer the next question, that turnaround can be much quicker. So I think there will always be some sort of the in the scientist realm or in some fields of engineering, there will always be some aspect of that, but now the layer at which you're doing it kind of changes. And I will say AI is really great for finding efficiencies in, taking a design and making it super efficient and cost effective. But to get to leaps in technology, you need innovation, right? And AI works by piecing together information that it knows about. To get innovation, you have to come up with things that nobody knows about. So I still think that the leaps, the jumps in technology will happen by people who are learning and go down to the core of the physics or chemistry of a particular subject in order to make that revolution.
Thank you very much, because this is one of the questions that I was thinking. Would AI help us, or would we completely leave it behind? But your answer gave us a clear picture on how we can take AI further as a supporting tool to achieve something, some bigger things. Thank you very much. I request Hafsa to ask a question.
Hi, ma'am. And firstly, happy morning. I happened to see the time, so I saw the time. It was 5:30, I guess. So it must be hard to get up early in the morning and deliver a talk. So thank you for
Just
that.
for us, yeah.
Yeah. So I'm Hafsa. I'm a grade 11 student, and I'm highly interested in this field of space exploration. So I was wondering what kind of internships we as students, high school students, especially from India, can get for experience into this field.
Yeah, that's an interesting one. I don't know that I have a good answer for you right now for high school students. So when I was in high school, I think there were a lot more programs available for high school students. There were specific high school student programs at places like Goddard and JPL. Many of those have actually dissolved, like they've stopped those particular programs. I don't really know why. There are some, and I'm sure there's programs in India too that I just don't know that much about. Um, there are like camp type programs where you get um, like a little bit of hands-on like project as well as exposure to different things. I know there's a NASA Academy program that is like that. There's one that's run out of Johnson Space Center that's like that. And I think most of the ones that I know of in the high school are not uh, limited to U.S. citizens, though there is a pretty broad set of people who apply, so it can be a little bit competitive. There is also girls in STEM international program that does something similar. I'm blanking on what the name is, but it was actually um, co co-organized by the U.S. Embassy in India. So I heard about it through the American representative at the Chennai consulate. So that might be a really good resource for you to use. The U.S. consulates, they have in their American center, they have resources that they can direct you to different internships and different programs. I'm not sure about high school, but I know at different levels they also do scholarships where the U.S. Embassy in India will pay for you to go over to the U.S. and have a particular experience. I know of one program where they were doing like an exchange between um, Indian Indian students and like German students, and they would go do, and they're not German, they were like tour the different NASA centers in the U.S. and they would come and tour the different centers in India too. So they have some programs like that. I'm not 100% sure ages of those type of things, but the American Center is probably a good place to start.
Thank you very much.
Thank you, ma'am.
I request Shloka Suraj to ask the question.
Hi, I'm in the 11th standard, and I'm really interested in space. So I had a specific question related to the satellite that you built in your undergrad. So what systems did you use for controlling the attitude of the system? And also, my other question was, how did you how did you map out your journey basically? Did you just figure it out? Or, yeah, how did you find that these programs existed?
Yeah, that's a great question. So the first one, the attitude system that I used for my undergraduate satellite, I built myself. So back in that day, CubeSats were just coming on, so there was nothing that you could buy to do the attitude control system. Now you can, there are whole like small companies that you can just buy a nice box and it'll do the whole system for you. But back in the day, I had to, we were using magnetometer and a torque rod. So a torque rod is basically a piece of copper wire that's coiled, that you run different current through it to generate a magnetic field. And when you're in Earth's sphere of influence, because Earth has a magnetic field, if the spacecraft generates its own magnetic field, it can act against the magnetic field of Earth, and you can get it to move that way. So my project as an undergrad was to actually design the coils to figure out how much current that you need to go through the wires, and actually like build a rig, build a mechanical system, and then hand wrap these coils onto the face plates of the structure to get it to work. Nowadays, you can just buy these like tiny little things that are that big to do that job. But back in that day, you weren't we couldn't buy anything, so I was designing it to do that job for it. In order, your second question of did I map out my journey? No, I did not map out my journey. Right, this talk is I created it after I landed on Mars, looking back and like picking out the things that that were pivotal moments, that helped me to where I am today. But when I was doing it, I didn't have a plan, right? Like I knew I wanted to do something in space, right? And that's kind of the broad bucket that I had given myself in. So throughout undergrad, it was all about, okay, what does it mean to do things in space? What can I do? So I was doing a lot of research on like what programs were out there, what sounded interesting, what I could do, and kind of grasping on any straw that seemed interesting. So I spent a lot of time on the internet, like just searching up different keywords to try to find programs. I spend a lot of time like talking to professors, to try to find any of the initiatives. I applied to way more than I actually got into, and it was a learning process, right? Like you apply to one, you're like, oh, okay, they want all of these different types of information from you, so maybe I should go make sure I have all of these. So it's a learning experience of trying and failing and trying again. And then for every opportunity that I did get, once I did it, I would take the time to say, oh, okay, what did I feel about that opportunity? Did I like it? Did I not like it? What did I understand? Do I want to do more? Or like, no, I don't really like that. I don't want to do that. So there were a lot of options like that too, where like I tried a bunch of things. Some I liked, some I didn't like. And the ones I liked, I kind of went in that direction and tried more things that were similar. And that's kind of how I made my journey. It's not that I had a fixed destination and in mind, but for every step that I took, I kind of reevaluated of like, what was it, something that I liked, didn't like, do I want to do more of, is it exciting, and took further steps along that path.
Thank you. Can I also get your email if I have any questions to ask?
So I have a website. It's drswatimohan.com, and there's a form on there that you can fill out if you have any questions. It'll come directly to my email. So anybody is welcome, if they didn't get their questions answered, you're welcome to fill that out and send me questions through that way. I can put that in the
Wonderful.
chat actually.
Yeah. While Dr. Swati Mohan puts it in the chat, you can reach out to her. Probably we'll take one last question from Ashrita. Ashrita, go ahead.
Hello, ma'am. I'm Ashrita and I'm studying in grade 4. Ma'am, I had a question, a specific question about one of your projects, the Curiosity Rover. So, ma'am, what was the main objective of the Curiosity Rover, and like, how did you come up with the idea of the objective, and what was your part in the mission?
So I did not. There are 5 Mars rovers so far. Sojourner was the first one that went on Mars Pathfinder. There was the twin rovers of Spirit and Opportunity, and then there was Curiosity, and then Perseverance. So I actually didn't work on Curiosity. Curiosity landed in 2011, 2000, 2012. Curiosity's objective was to search for the building blocks for life. So it was looking for the carbons, the nitrogens, the amino acids, that the elements that you need for life, in addition to water. Once Curiosity made its discoveries that there are all the building blocks for life, we basically had the check mark of, okay, with Spirit, Opportunity, Curiosity, we found that in the past, Mars was a very wet, warm and wet climate, that it has all the building blocks for life, that it had not just water, but liquid water, neutral liquid water in the past. So the idea was, with those missions, they basically got to the point where, well, there was probably life in the past. It has all of the ingredients for life to have existed in the past. Not now, it doesn't have those ingredients now, but in the past. So Perseverance's role, which I did work on, was to design a rover to go and find signs of life. So we're talking about not little green men, probably not even microbes, but there are certain like processes for life that will actually have impact on the geology. So like you can go in like Australia and see some of these features where, because of like single-celled organisms and things like that, they will actually create certain types of rocks or certain type of features associated with life. So Perseverance's role is to find those signs of past life. So to pick rock samples, to pick sediment samples that we think can retain those signs of past life on Mars. So Perseverance went to a place called Jezero Crater, which we think is an ancient lake bed, basically. Like there's a really nice like river channel that flows into it that looks like a big lake bed, where it has like the shallow part of the lake and then it drops down into the deep part of the lake. So by going there, you kind of get multiple different areas. You get like the deep part of the lake, you get the shallow part of the lake, and then you kind of, Perseverance is now climbing up through the river channel into like the inlet flow of that lake.
Thank you, ma'am. It was really nice interacting with you.
Thanks.
Dr. Mohan, if you don't mind, we'll take one last question. Actually, there are 2 questions, and I would like to merge them, and then you can answer them together. So this is question by Revati Mohan and Srikanda. I would let you both to tell your question together, and we would get an answer Yeah, Revati, you can go ahead.
Hello, doctor. Thank you, Nikita. Thank you so much. Good morning, doctor. It's a pleasure to know about you, and it's a absolute pleasure. I'm getting goosebumps and butterflies knowing your story. And yeah, and doctor, my question is, how do you handle your challenging days right from your Kennedy station to the NASA? Because as you mentioned, since you have a lot of supporting system, your family and friends are there. But how open people at well-educated and well-established minds access the mental health support? Since it is a taboo word. For example, I have done a research on aviation psychology and I published a book on aviation psychology too. And last year I went to Dubai Air Expo. I met a couple of astronauts and I complimented the first copy to them and they said, Revati, when is your research on space psychology? Why aviation psychology? I was
Yeah.
flabbergasted, and I just want to know your opinion in this regard because to know the psychology of the astronauts, we just want to know to get to know about their through their interviews and their biographies. So I just want your opinion in this regard. Can I get an internship on aerospace psychology at NASA? And yes. As I said, I don't have any map in what I'm doing, but I'm doing something, and I need your opinion, doctor.
Yeah,
That's a
we will,
great field. Oh,
we
sorry.
will also take the other question, Doctor, if you don't mind. Sri Gandha, would you like to go ahead and we could get an answer, combined answer? Sri Gandha, are you there?
Yes, ma'am.
Perfect.
First of all, thank you for such an amazing session, ma'am. Truly grateful for you. So my question is that I believe that you had an US citizenship before working at NASA. So how difficult it is for the international students who complete their masters in the US? So how difficult it is for them to get a full-time job at NASA? And is PhD mandatory for all those students who completed their MS in the US?
Dr.
Um,
Swati, over to you. If you could
okay.
combine and answer, that would be great.
So in terms of the space psychology, that's a really interesting field. The astronauts are their their own classification of people. I don't know of internships, but going through like aerospace medicine, there's some organizations that work with them regarding aerospace medicine. There's another field about the psychology of teams. There's a professor, I think she's at Johns Hopkins or Georgetown or GW, George Washington University. Her name is Janet Vertesi. She does psychology of teams. So she's done work with NASA on the psychology of working groups and what the missions need, that sort of thing. So she might be a good resource to start with in terms of that area. I don't know about psychology and internships. Like you'd have to find it through one of these paths if they were looking to do things. But there might be opportunities to work with as like a shadow if you came with your own funding that you could get some research. They're pretty tight-lipped with the astronauts because uh, it's hard to publish any data. There's such a few set of astronauts. It's hard to publish any data without making it very personal to them. Like you can figure out very easily which astronaut it is. So I'm not sure about that, but if they're willing to do it, you can probably um, get some information directly to them on how they deal with it, because that's a whole nother field of study. How how I deal with the challenging days. I mean, even though I never go up into space, like it can get very challenging just to do the regular work for an interplanetary mission because the launch date is fixed, right? Like you know what that launch date is, and you're trying very hard not to slip because you need all the planets to align in order to launch on that day. So all the work has to get done. So there's kind of this huge wave of work that happens like towards the launch date that gets more and more um, intense. So it becomes a lot of shift work, a lot of long hours. And once you're in operations, because the spacecraft can only talk when it's in view, like the hours fluctuate. So it's not a 9 to 5 job at all. Some nights I was working, 11 p.m. to 6 a.m. Some nights I was working like 1 a.m. to 10 a.m. Like it kept changing. And it's hard biologically on you when you keep changing what your sleep schedule is, right? Because you get more tired, and working through that, especially with a good support system, is really important. Um, the second question on international students obtaining a full-time job after master's, it is harder at NASA specifically, right? Because NASA is a government agency. So at NASA Center, to be a civil servant, it's a little harder. At JPL, there are other opportunities since we're not NASA employees, we're Caltech employees. So there's more opportunities, especially for like postdocs. And on the science side, it's a lot easier because um, the science and the data analytics of science instruments, because they tend to work with more international partners, and they're more public domain. It's a lot easier to get into it on that side for international students. It's harder on the like spacecraft build portion because so much of that is close to like military spacecraft build that there's criteria in place. I I don't think a PhD is mandatory, but I will say most of the people that I know who have come and worked for NASA, their advisor had very strong ties to a particular NASA centers, or they trained in a particular way to make them much more um, appealing, or like a very niche field. Those are the ones that I know of where there has been multiple who have come from a particular lab. So because because you're there with an advisor longer for a PhD, especially if they have a grant already um, in the space field with a particular NASA center, you kind of have a longer time to become a known quantity. So I think it's easier when you have a PhD, but I don't think it's required. That being said, there's also a lot of startups coming up that have a little bit more flexibility in hiring than NASA would.
Thank you very much, Dr. Swati. Actually, in every talk, when I invite guests, I usually ask question, and one question that I usually ask is, what is that you tell the students? What are the three major takeaways? In fact, you ended your presentation with the three takeaways,
Yeah.
but we all get into one situation in our lives, be it whatever age we are in, that certain point of time we feel like, okay, we are, or I'm just unable to go forward. But I know that I like to do, I'm just unable to move forward. So for all of us, when we are in that situation, what is that you would suggest we all do? And if you could tell in like 2 lines, what is that you would want all of us to do?
JPL has a motto um, that it's kind of stayed with me, and it basically goes. Let me share it. Um, it is far better to dare mighty things, to win glorious triumphs, even though checkered by failure, than to rank with those poor spirits that neither enjoy nor suffer much, because they live in the gray twilight that knows not victory nor defeat. I take this to mean that no failure can be worse than regret. That any, even if we try and we don't achieve it, at least we will have that knowledge definitively that whatever it was that we tried, we gave it our best, and if it didn't work out, it didn't work out. But to live in that great twilight that I could have, should have, would have, that haunts us forever. With the failure, at least there's something tangible that you can understand, that you can learn from, that you can work forward, move forward from. For regret, there is no such thing. So I would say the going is always hard, and it can get harder, but to remember that time, that at least, even if you slow down in those hard periods, at least you keep trying, because if you give up, then you'll never know where you could have gone, and that will haunt you for a lot longer than the failure will.
Thank you. Thanks a lot for sharing that. I hope everyone heard what one must think when you are in that situation, and it applies to everyone. Dr. Swati, again, I'd like to thank you for giving time, and it's not a normal time, so I'm more thankful to you for spending time with all of us and sharing your journey and about the missions, and also taking time out in answering every question that we had. Thanks a lot from Gen X, from SSERD, from all the participants out here. Thanks a lot.
Thank you. Thank you for having me. And I put the website is in the chat, so if there are any other questions, feel free to use the form on that website to send them to me.
Perfect. Thank you very much. We will now end this session here, and we're also going to stop recording. Yeah. Again, to everyone, thanks a lot for joining. I see you all again in the next talk, next session. Take care. Bye bye.